Thank you. So I'm Logan with Argyle, and we're talking about in what way is AR a feast for AI. To get into it, I want to go back in time a little bit just to get some perspective on where we are at this moment in time. Old XKCD, everyone's favorite. This is the kind of conversation I have at work a lot where the CEO will say, all right, we want this, and I'll say, great, that'll be ready in an hour. And this one, and check whether the photo is of a bird, I'll need a research team and 5 years. It can be hard to explain what things are easy to do in technology and what things are nearly impossible. But here's the thing. That comic was 10 years ago. I'm sure there's people in this room who were already in their professional careers 10 years ago. And that is already very different. So as a way of demonstrating just how far we've moved and how revolutionary of a moment this is, I did where I asked ChatGPT. We had a little conversation about this where we said, oh, no worries. We said, all right, what kind of model we want to do this? We went and grabbed some pre-existing computer vision models, pre-existing data sets, and we were able to write out all the code to train a torch vision model for this and train it in 30 minutes at my own desktop at work. We are not just able to now do what was impossible, but we are able to do something that we didn't even know to ask the question was impossible and have it do something impossible for us. That's where we're at right now. But if that amazing stuff has happened, where are we now? Why hasn't AI solved all our problems yet? And that is because I think we've got the hardware we need. We've made great strides with algorithms, but when you want to move beyond just a stunt like I did, when you want to do actual useful work, that's where we get to the problem of the labeled data. Because when we have real customers with real problems, we need very specific kinds of data. Here in this room, this is an augmented World Expo kind of crowd. We probably have a lot of spatial problems, and those problems are not going to be well represented in the existing open source data sets, and those data sets aren't going to touch what our customers actually need to do. So when we're trying to get these data sets, quantity is great, quality is absolutely necessary. This is an issue of garbage in, garbage out. So it becomes an extremely costly challenge of how do you generate the data to train the AI models, and then how do you label it in a way that is actually intelligent, correct, and useful for your customers. And this gets us to our big thesis, that the augmented reality devices we're using and the augmented reality applications that we are building already include within them the ingredients to make really, really valuable data sets that can do, I'd say, a shocking amount of work for us. I think this is an extremely underutilized resource in our industry right now. So to get into some specifics, to get into some examples, and we are definitely going to get into the weeds because that's where I like to live. I'm going to introduce you to my company. We've got a video here. We're doing the backup version. Can we switch over to that? Great. So this is Argyle. We're all about overlaying large data sets onto large sites. We built this originally with construction in mind, like the general contractor, but then have found a lot of this demand in large manufacturing facilities, other kinds of industrial uses, frontline work. And so this is actually a 2-mile-long building here, enormous space. While I was there on this trip, we didn't augment the entire thing, but we're talking about big industrial data sets that are metadata rich that we put onto the site and keep them aligned one-to-one as you move through the space. Oh, let's switch back. Perfect. So in order to really get a handle on what that particular, that alignment of that data grants us, just a quick review on what we're actually talking about when we're feeding these models. I'm speaking mostly about computer vision right now, because again, that's one of my current obsessions. This is classic history of computer vision training, the minced data set, which was, I think, one of the first and biggest examples of how you can use trained neural net models to do things that you just can't program. So it's a large data set of handwritten numbers. You can't write a rule set to recognize all those numbers. So we assign each pixel a single number between 0 and 1, line them all up, connect them all together, and just let it try to guess the number. And of course, every single one of those examples has a right answer. So while you're training, you give it the input, tell it the right answer. It says, oh, in what ways was I wrong? And then it learns and develops into something that can actually solve the problem for us. However, it doesn't have to be as simple as that. So already, if you have, say, a color image, you have multiple layers of information here. The red, the green, the blue are all different channels that you're feeding into this on top of each other. And we don't have to stop it there. So this is an example. On the left, you have a view from our application. This is what the user is seeing. You can see it's mostly they're seeing the real world because that's what they're working with, that's what they're walking through. And you can see that there's just outlines on those different parts of the building. And then over on the right, this is output of shaders that we have within the application that can feed additional data without the user having to see it at all, without that being in the user's face. It can feed that data, save it out, just for the purposes of training the AI models. The data we're talking about here is this BIM data. In the architecture and construction world, that's building information modeling. Instead of just being like a mesh, this building is all the different elements. They all know what they are. They all know, they've got their location. They've got their geometry. They have metadata about materials and heat flow through them, and has it been installed and by who, if that's something that the user chooses to put in there. And all of that data is available to us if we then want to be able to pull that data out and use it to train a model. Let's talk about, actually, I do want to go back here. Let's talk about what we can do with this. So this part is only the data that our customers are passing to us or passing into the application, that they have built these models. But if we are trying to, say, do one of the gold standards of architecture construction is scan to BIM, one of the big problems is how do you get a really large data set of this is the scan and these are the BIM elements. And this is able to gather all of that, layer on all the information about what's actually there, and deliver a pseudo-generative, I would say, ability to just create those BIM models after walking on a site. So jumping over to a very different kind of data input is user actions. This gets at a similar kind of benefit to one of the early examples of really useful work that computer vision was doing. You probably heard about AI radiologists. It's not really replacing the radiologist, more like what the previous presenter was talking about, the centaur idea where you are working together with the AI. In that case, they had radiologists look at x-rays, identify probable cancerous tumors, and then when they did surgery, remove those, they could correct any mistakes there and use those images as well as the correct answer to create a model that actually could outperform radiologists on those early detections. We have situations like that all over the world where it's difficult to gather all of that information without paying experts in the field to sit there and label your data for you, which it doesn't pencil for most companies. But this is a situation where if we can make it useful enough to the user, and this is key, make a feature that they actually want to use that also tags potential issues, it not only means that they're automatically generating data for you, but the fact that this is done in augmented reality means that once you tag a location, as you continue to look at that, as you move to the left and move to the right, it can keep snapping picture, 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 picture. And that entire time, you are getting a broad spectrum representation of that same issue. There's one of the techniques in training computer vision is something called data augmentation, where you kind of have to take a small data set, fake it to make it bigger by rotating it, by scaling it, by adding grain to it. In this case, we have a much more honest and accurate kind of data augmentation because you're getting truly unique views of the same problem by putting it in a 3D location so that the app always knows where to look and when it's seeing that issue. Now I want to talk about some of the sort of techniques that we've learned. I think there's a video on this as well. It's just short. But in this challenge, we see QR codes in our app, and we didn't find a good enough cross-platform QR viewer that can actually guess the position of the QR codes really precisely in 3D space. Our customers are expecting sub-inch accuracy everywhere, and in important places, quarter of an inch is what's expected. And cross-platform QR, that wasn't really possible. So we are working on a neural QR pose estimator. In doing that, we have placed QR codes around our office. We walk around with an AR headset, look at them from every angle, and it gets really, really good at finding the QR codes because, similar to when we've marked up those issues, we mark up where those QR codes are, and it's always getting the right answer. That is the very best way to make it accurately predict whether the QR code is there. And then to really, really nail the precision, this is where we can bring in synthetic data. Because synthetic data, while it's not as high quality an image, the location is perfectly accurate. The big difference between just taking a picture is a human couldn't decide to annotate a picture after the fact where the camera knows exactly where it is relative to what it's looking at. That's something that you can only do with augmented reality or with synthetic data, and we found the most success when we are combining the two together so that we can get both accurate discovery and precision. A slightly different take on this was actually when we were trying to build a prototype where, with a single camera, we could estimate depth. Now, this is something that people have been doing computer vision for a long time. You take a photograph, and by feeding in a lot of that, the models can see what's in the room. You see a hallway going down. You see something in the foreground. You guess that one is closer to the other. But with simple visual cues like that, you can't get dimensionally accurate depth. And so we have customers in places that don't laser scan well. And so we needed to be able to guess that the depth of everything for model reconstruction accurately in a way that is mathematically deterministic, and that's why we use stereoscopy. But the AI was working too hard trying to go with the visual cues, just like traditional AI, which is why we set up this nonsense as our synthetic augmentation to the augmented reality version of this. By including just this noise, this is impossible to guess without two pictures next to each other, offset, giving us that stereo view. And so, again, with synthetic, teamed up with augmented reality, we could get something that both understood the world well, and we could get that precision that we needed, or solving things where it's an impossible view, right? I've heard of other developers using synthetic when it's a situation where they need to predict things that are dangerous as well. Another lesson here is the equipment that you're using. So I'm talking about using augmented reality to capture this data, but depending on what information you're trying to capture, it's extremely important to choose the right tools. While an iPhone has an excellent camera, it's a very high-quality picture, it's made for consumer usage. It has image stabilization. It's got, it's already doing a bunch of things to change the image, and the tracking on a phone is just never going to be good enough if you need really good, solid position and spatial information. So whenever we are pulling data for training any kind of spatial AI, we're always using the Magic Leap 2. Among any of the headsets or tools out there, we've found it to be by far the most dimensionally accurate over distances. The tracking is just better than other headsets. To get any better than that, I think you would need a robotic solution where it can count wheel turns and things like that to get any more accurate than what we're getting out of the Magic Leap. Last thing that we cannot get out of here without hitting is you can definitely start to imagine there are some serious ethical concerns, security concerns. I'm sitting here talking about, hey, it's going to be great. Our customers are going to be training our AI for us. They're going to be giving us all their data. We cannot get ourselves into a world where we are tricking our customers into giving us data they don't think they're giving us. That's going to get us in trouble. That's going to make the world a worse place. So we need not only the consent of our users, but these are outward-facing cameras. We need consent of any people or their property or intellectual property that is also included within that data that we're getting. Another thing that we don't think about a lot is the protected IP of this, where our customers, the models that we are seeing, many of them, we have to be under NDA to even get those into AR. And if there's any way that we're training our models that can then accidentally pull that protected IP of the design of their buildings or factories and get it into some future product, that's going to be a problem. So it's incredibly important whenever you're designing these systems to make sure you've got consent, make sure you've got that safety. And that's it. Thank you. I'm here for questions. I think we have a few more minutes.
We do have a few minutes. Who's got questions? Right here up front.
For the synthetic data, in the stereoscopic image that you showed, how do you approach that, and what was that image? So.
Right. Okay. So whenever I basically have a system that I have set up that is just a pipeline for generating data in AR, and then a pipeline for generating data synthetically. In the synthetic version, it's a lot of what I have in AR, except I have to include randomizers for everything. So when I'm walking around a space, I'll make sure that I move chairs around and turn the lights on and off as I continue to snap more pictures. In the synthetic version, I try to randomize everything as possible to make sure we don't get any kind of overfitting. And so that one, whenever I hit play, it makes a bunch of random objects all around the space. Those objects have a randomized texture on them that offsets amongst itself randomly. So every time you push play, the texture is random, the scale is random, the objects are random, and the camera movement is random, which is just systems that I've built to automate that so that I can hit play, go to lunch, come back, and have 30,000 images that are all unique each time. Did that get at what you're asking?
Yeah.
Yeah.
Fantastic. Another question over here.
Yeah, so my question is more in the line of what kind of model do you use for those kind of object detection? Like you use YOLO kind of model or something else?
Yeah, so in this case, whenever I'm doing this kind of spatial model building, I'll basically follow inspiration from like a YOLO model, but I find that because the data that I'm bringing in is so different from what an old-fashioned YOLO model is bringing in, because the old-fashioned YOLO model doesn't have position and pose and all that information from the AR camera. So basically, I model the architecture after that, adapt it, and then usually train from scratch. And it was very similar to YOLO for the object detection work. And then some of the other work was the depth finding one was more of a UNet architecture.
Thank you. And we have time for one final question.
You mentioned robotics as a possibility for like heightening precision. Are there other? First of all, have you done that, and are there other like implementations for robotics that you find useful in this kind of mapping?
The only reason I would go to robotics would be for a situation where humans can't really go there very well. For example, the video that you saw earlier of our app working was in a particle accelerator that was only temporarily accessible by the humans. And so one of the proposals we've talked to them about is basically putting a Magic Leap onto a robot dog to walk around. So that way I can just reuse the same code we've already been doing. I don't have to fuss about doing the robotics myself and just still rely on the tracking of the AR device. And getting a cool story. How sci-fi is that? No.
Awesome. Well, I lied. We have 1 minute and 50 seconds left. Is there one other question that hasn't been asked already? Yes, in the back.
From your perspective, what are the biggest privacy issues that your field is going to encounter? What they are?
I think that someone doing similar work to me, but to a consumer, would have very different privacy issues. I mostly worry about the enterprises that we work with and making sure that their proprietary data is extremely safe. So, yeah, like we've heard the examples of ChatGPT including things that were kind of should have been protected that came from training data of using ChatGPT. Also, watermarks going on to generated images, things like that, where the invasion of privacy or intellectual property control actually got baked into the model. That's, I think, one of the things I worry about the most because it would be the hardest to notice because of the black box nature. And so I think that the best way around that is to be very careful about your training data and make sure that you are not training, like not only an opt-out option, but I think we need an explicit opt-in option where maybe we can make a deal with our customers saying, is this publicly available? Can we give you a discount to include your images from your site into our training?
Fantastic. Well, can we thank Logan again for a very insightful